Hi guys. Carol asked me to put together a quick review of the class. So we covered a lot of material. I'm going to try to just breeze through it all so it doesn't take too long. But I'm just going to go through essentially what was your midterm and final reviews. I'm hoping that this is helpful. So without further introduction, we'll just jump right into it. Um, Three of the main objectives of a radiation protection program are to focus on when radiation is justified in use. You need to be confident that the benefit is going to outweigh the risk, because there is always risk with radiation exposure, and generally higher risk with higher exposure, which is another reason why you want to optimize. If you do choose to use radiation, you want to optimize its use. You don't want to image with more radiation than necessary. One, because you'll get a bad image, and two, because you'll give more dose to the patient. You can customize protocols to patients to give them better dose. We see this a lot in pediatric patients. They don't need to be imaged with a protocol that's meant for an adult because their bodies are different. And you can get a lot lower dose if you do that. And finally, just work to limit the overall risk from the use of radiation. Sorry, I got to put it into presentation mode. So the actual, so much of health physics deals with the idea of risk and quantifying risk. And that's why remember the unit of the rank and equivalent man, or the REM. It's important to remember that the REM is a unit of risk. It's not a unit of dose. It is a unit of risk that corresponds to a certain absorbed dose that we'll get into a little bit more. But the idea of annual limits and such are to put the risk factors for people working with radiation in a similar, level of other occupations that also have some risk. Every job has a little bit of risk, some much more than others, but they try to put the occupations that deal with radiation in a similar ballpark as the average job, I would say. And also remember, annual limits, just because you can reach annual limits doesn't mean you should. There's always that a law or a principle, as low as reasonably achievable. So remember cell radiosensitivity. Not all cells are created equal when it comes to radiosensitivity. You have that law of Bergioni-Trivendo that says that cells that divide rapidly, divide for a long time, unspecialized cells like stem cells, those are going to be the ones that are most sensitive to radiation damage. And the damage from radiation comes in two forms. You have the non-stochastic, also known as deterministic or threshold effects. These are the ones where, where past a certain dose, you expect to start to see them. Something like skin reddening, skin ulceration, sterility, things like that. That's contrasted with stochastic effects, which are the effects that you have a higher chance of happening with more and more dose. And really, when we talk about that, we're talking about cancer. Cancer is the main stochastic effect. The only other stochastic effect would be potential genetic defects that are passed down to future generations. However, that's not seen in humans. Doesn't mean it doesn't exist. It just means that it's not a very pronounced effect. So really, we focus on the future risk of cancer when we're talking about risk from radiation. The linear no threshold is the prevailing model for radiation exposure, and in terms of risk versus radiation exposure, it says that it's linear, essentially from zero. Every little bit of dose comes with a little bit of risk. This comes from the knowledge we have of people who have received large doses of radiation. Problem is, these people are predominantly people like the atomic bomb survivors, who were their exposure situation was one big blast of radiation at once, versus that chronic low dose exposure that is more common in the occupational setting. So there are key differences, and we know that most cancers don't follow a linear no threshold model, but for the purpose of dose limits and such, it's thought that it is the best model that we have. We talk about radiation units. It's important to understand at least SI units and the US units, understand that both are used, what they mean. A Curie is the US unit. It's an incredibly large amount of activity versus the Becquerel, which is a very small amount of activity, 1 disintegration per second, versus it's 37 billion disintegrations per minute for a Curie. We also talk about the different types of measurements you can take in radiation. Remember this graphic of, you have a source that has a certain activity. That certain activity gives off radiation that then ionizes air, and that's known as exposure. You can measure the exposure. It's actually the easiest to measure exposure, but that is used as a placeholder for, someone, a person standing in that radiation field. They're going to get some sort of absorbed dose from that exposure. They're not exactly equal, but they're generally pretty close. And then that dose equivalent takes that absorbed dose and applies some sort of correction factor for the type of radiation that was present, and gives it that REM value, or that risk factor, the REM or the sievert. We talked about conversion from sieverts to REM and back. We did a lot of tedious homework calculations on this stuff. It's important to know the prefixes and what they denote. Really, the common ones are going to be the micro, milli, kilo, mega, and giga. Depends if you're talking about SI units or US units. It's good to know at least the ones that are more often used. So radioactive decay, that's the essence of where this radiation is coming from. It's coming from unstable atoms that are decaying and releasing energy. It's important to remember that photon radiation does not fundamentally change the atom. That's just excess energy leaving the atom. You need to have some sort of particle either emitted from the nucleus or drawn into the nucleus to fundamentally change the atom. And that's what will create that stable element, or create the decay series that ends in a stable element. Every isotope has its own half-life. It can be very small. It can be very large. It could be fractions of a microsecond. It could be billions of years, and everything in between. But for the most part, the medical realm, we use isotopes that have half-lives from minutes to weeks or months, because anything much longer is not really practical, and anything much shorter is not really practical. So as I mentioned, the unit of exposure is the Rankine. This is most commonly what our meters that we use, our dose rate meters, are measuring, because they are gas-filled detectors, they're air-filled detectors. So they're measuring the ionization of that air. Remember that exposure is only really used for photon radiation. It's the ionization of the air, a certain volume of air. And it's used as a placeholder for absorbed dose, because absorbed dose is a little trickier to measure. Absorbed dose being, energy absorbed per unit mass. And so for humans, it's 98 ergs per gram in tissue. So that's, pretty close to that 100. It's a pretty close conversion factor. But when you're converting from air to tissue, you need to take into account this discrepancy between the two numbers. Dose equivalence is taking that absorbed dose and then multiplying it by that quality factor or radiation weighting factor. And that will give you, because remember that something like alpha radiation or neutron radiation, for the same amount of absorbed dose, will have a higher dose equivalent. It will be more biologically damaging. So that's where these factors come into play. Annual dose limits, that's going to be something that's pretty important. I would not be surprised if you are tested on this in your boards. Just remember the dose limits. There's no way to get around just memorizing them. You should know them in rem or sievert or millirem and millisieverts, but it's your whole body is at 5 rem, and then your organ or shallow dose, organ skin dose, is going to be the 50 rem, so 10 times more. When you declare your pregnancy with the Radiation Safety Office, your limit drops from 5 rem to 0.5 rem or 500 millirem over the course of your pregnancy. And then the member of the public is the 100 millirem, much lower, because they are getting much less benefit out of this exposure. Someone coming in to visit our hospital is not being paid. It's not their job. So we want to make sure their exposure is minimal. So there's different types of dose equivalents that we go through. Your dosimeter is measuring different things. If you have a ring dosimeter, that's measuring, an organ or extremity dose, because sometimes you're in a situation where you're manipulating a source behind a shield. So your whole body would be shielded quite, probably pretty extensively, but your hands are still subject to sometimes a very large amount of dose. So that's where the ring dosimeters come into play. But your dosimeter that you wear, your whole body dosimeter, is measuring deep dose with a series of filters in place that measure the actual energy of the radiation, the depth that the radiation gets to. So deep dose is measured at a depth of 1 centimeter in tissue. That's considered a placeholder for anything that is deeper than 1 centimeter. So that measurement at 1 centimeter would be what all your organs are theoretically getting. that's not the actual case, because the deeper the tissue, the less radiation reaches it. So it's a little conservative when you talk about deeper organs, but for the sake of simplicity, they treat it as 1 centimeter or deeper is your deep dose equivalent, and that's what your dosimeter measures in that regard. Shallow dose is going to be either your extremity ring badge, or there's also other filters in the whole body dosimeter that measure shallow dose as well. So those are both measuring it, and some combination of those numbers is what goes on your badge record. This has that 50,000 millirem limit or 50 rem limit. And then the lens of the eye is treated differently than other organs, solely because of the known risk of developing cataracts from radiation exposure. So there's a lower limit than other organs. It's also a different depth, just to mimic sensitive structures in the eye. So this is a good slide. It's a good summary slide talking about the depth that the dose is measured at and the limit for that specific dose. So tissue weighting factors they kind of recognize that fact of radiosensitivity, that certain tissues are much more radiosensitive, meaning that when you're looking at that stochastic risk, that, essentially that whole body risk, if you have certain organs that are irradiated, for example, say a radiopharmaceutical that selectively goes to certain organs, these tissue weighting factors take that dose to that organ and kind of expand it to a whole body risk of developing cancer. So a tissue that is very radiosensitive, that is more likely to develop cancer, would have a high tissue weighting factor. So if you have a patient that receives a radiopharmaceutical, you have a good idea of where that goes, how much dose per activity goes to these organs. You can sum up all the doses to the individual organs times their tissue weighting factor, and that gives you an overall whole body dose. So that would be this right here. That would be your total effective dose, would be that committed effective dose equivalent, which is the sum of all the individual organ doses and their respective weighting factors, in combination to your deep dose equivalent, which is that dosimeter reading, because if you have some internal exposure, it's going to radiate your insides, and that deep dose external exposure is also radiating your insides. So your total effective dose equivalent is what compared to your badge limits or your annual limits. The total organ dose equivalent is that individual organ that has a certain dose, and then you combine that with the deep dose to get the total organ dose equivalent. And that would be against your 50 rem limit. Your committed effective dose equivalent is really just when you have an internal exposure. The second something goes in, you're committed to it decaying with the physical and biological half-life. There's limited ways that you can actually get them out of your body, versus like an external exposure that you have options. You can shield the source, you can get away from the source. But once it's inside your body, it's a committed dose, and the committed dose equivalent times the tissue weighting factor for where it's actually going gives you your committed effective dose equivalent. And that's what goes into the internal aspect of your total dose. And then remember the annual limit on intake, that is really that's a value, that's an activity for specific isotopes. Every isotope has a different alley, but it would be the amount of that isotope that needs to be ingested or inhaled to hit one of these limits. If it's something like a radioiodine that selectively goes to the thyroid, it'll generally be an activity that gives you a thyroid dose of 50 rem. But a lot of other isotopes have just an activity that will give you a whole body dose of 5 rem. And these are found under 10 CFR 20 Appendix B. There is a list of all of them. If you're interested in reading it a little more on what the alley is, something we use a lot in the radiation safety office. Probably less so for you guys because your concern is more external radiation. Background dose, background radiation is everywhere. It comes from space, comes from the makeup of Earth, comes from man-made nuclear fallout, from above ground atomic bomb testing, and finally just, medical sources. And then the internal aspect also comes from a lot of these, but to a lesser extent. Cosmic rays actually activate materials on the ground, in the air, in human bodies. Potassium is just a primordial element that's been around since the dawn of Earth. And the percentage of potassium is naturally radioactive. So anywhere you have high potassium, you have some radioactive potassium. The biggest That's actually the highest radioisotope we have in our body, the highest activity. And then radon, we discussed radon, how it's a radioactive gas. It comes from the decay of natural uranium in the ground, comes up out of the ground because it decays to a gas. If you breathe it in, some of it will decay while it's in your lungs, and it goes from a gas back to a solid, and then that is deposited in your lungs, and that will give you a dose, a pretty high dose. And that's radon is the highest natural source, and medical x-rays is the highest man-made source of background radiation. So right here, you can see that it's been going up, background radiation, and that's primarily the medical component. You have diagnostic procedures like CT scans that are used a lot, very helpful from a diagnostic standpoint, but they also have a lot of dose with them. So this number still holds true for the most part. An average background is about 660 millirem, pretty even split between natural and man-made sources. So that's something that you could definitely be asked to know. And you compare these levels with levels that actually cause those threshold or deterministic effects. So these are orders of magnitude higher than background levels. So these are situations where you need to be exposed to a lot of radiation in order to start to see these things. So we talked about the actual physical makeup of the atom, the nucleus, protons, positively charged protons, neutral neutrons, orbited by a negatively charged electron cloud. The atomic mass is simply the number of protons plus the number of neutrons. This only holds perfectly true for carbon-12. It's based off of carbon-12 because of just the subtle changes in binding energies of the nuclei for higher and lower atomic mass elements. It's not a perfect number, but for all of our purposes, it's close enough. So iodine-131 has an atomic mass of 131. Things like that. But the atomic number is simply just the number of protons, and that is what dictates what the actual element is. If you change the number of protons, you change the element. Remember, so a lot of the isotopes that we deal with are shown like this, with the Z is the atomic number, A is the atomic mass, and N is the number of neutrons. So X is the actual element abbreviation. Yep, there you go. We talked about isotones, same number of neutrons. Remember the tone, the N, so it's the same number of neutrons. Isobar, same atomic mass. Remember barbell, working out, so atomic weight. And then isotopes, you got the P for protons. Isotopes that's really the one that we use all day, every day. Never had a situation where I really needed to use isotone or isobar, but isotope is very, very important in terms of radiation safety, because different isotopes of the same element can behave very differently. So you have to be familiar with all the isotopes. The element itself kind of dictates how it behaves chemically, but the isotope is how it behaves radioactively. The different types of radiation that you can be exposed to, very important to know, because that's the only way you can actually be safe around them. Alpha particles are a large particle. It has a large mass, has a large charge. So it has, high potential for biological damage, but only if it's ingested. It actually does not have enough energy to actually get through your skin. It can't even reach healthy skin, living skin. So it does not give you any external dose, but because it's it interacts very readily. So if it actually gets into short distance contact with sensitive tissue, like being inhaled in your lungs, it can give very high doses. Beta particles, also known as electrons or positrons, are also particle radiation. They have smaller mass, smaller charge though, so they have a little bit more range. They can be an external hazard. They're all internal hazards. And then you have the photon radiation, which has no mass or charge, much less likely to interact. X-rays come from the electron shell. Gammas come directly from the nucleus. These are the ones where you need, large amounts of lead potentially to actually shield, whereas you can stop an alpha particle with a piece of paper. You can stop a beta particle with a thin sheet of plastic or you can stop it with a thin sheet of lead, but then you'll create a lot of X-ray radiation. And then finally, you got neutron radiation. Really, one of the few places we have neutron radiation is in the Linac faults, the high energy Linac faults. These are hard to stop because they have no charge. So you have to physically stop them with similar sized particles. So that's why you see a lot of plastic as a shield, because plastic has high amounts of hydrogen atoms in it. So when you have a neutron and you have a hydrogen atom, when a neutron hits a hydrogen atom, it gives a lot of its energy to that hydrogen atom, versus if you have a neutron that hits a lead atom, the lead atom is significantly larger. So it kind of hits it and just bounces right off, and it doesn't lose much energy. So that's why the high hydrogen atom content shielding serves to slow those neutrons down so they can eventually be captured before they work their way out of the vault. Okay, yeah, so I kind of just went through all this stuff that's here. It's good just to keep an eye on all these. So alpha particles, high kinetic energy, low velocity. If you think about all these particles, when they are leaving the atom and interacting with the world, they're flying through a sea of electrons, essentially. Space, matter, whether it's air or solid matter, is essentially a sea of electrons. So electrons are small, negatively charged particles. So if you have an alpha particle flying through that, it's just going to be drawing all those electrons to it, pulling it, ionizing the atoms that those electrons are coming from. But it happens very rapidly, so they stop. A beta particle is going to be pushing those electrons away. They're going to be similar size to the beta particle because they're all both electrons. So either ionize or excite. Ionize being stripping the electron away from the atom, or excitation being it just excites it. And then once that decays back down, it releases an X-ray. Bremsstrahlung radiation, very important because it's the basis for all X-ray machines. So in that situation, it is useful. But in a situation where you're shielding from a high energy beta source, you do not want Bremsstrahlung radiation. You try to minimize that production because that would just mean a higher dose to you from X-ray production. We talked about the electrons. Photons. I think, yeah, so the three interactions of photons is the photoelectric effect. That's where the actual photon is absorbed by an electron totally. That electron takes that energy and goes off into space to interact with, further electrons somewhere else. This is common in low energies. And, the higher the atomic number of the matter, the higher the energy that this is possible. So something like lead has photoelectric effect occurring up to energies 100 keV or beyond, whereas less high atomic number materials will have lower energy thresholds for photoelectric effect. They're more likely to Compton scatter, and that's where the electron interacts, or the photon interacts with an electron. It gives it enough energy to break its binding energy and to go off freely in space. It ionizes it, but it also creates a secondary photon of lower energy that also continues on its path. And then finally, pair production. Pair production needs a minimum energy of 1.022 MeV because that is the equivalent of the rest masses of an electron and a positron. So that's a minimum energy that you need. But in real world, you actually need a lot more energy for it to be common, for it to actually happen. So it's, this happens in conjunction. Even when you have photons above this energy, more often than not, it's going to be Compton scattering until you get to very high energy photons. But what that happens is that photon passes near a nucleus and spontaneously turns into a positron and an electron. And so that electron goes on its way. That positron will go on its way interacting until it loses all of its energy, at which point it combines with a local electron and annihilates into pure photon radiation. Neutrons, like I said, slow neutrons are generally just absorbed by an atom where they'll kick off a gamma ray. A fast neutron really needs to bounce around and lose its energy before it actually can become a slow neutron and then be absorbed. We cover decay. You guys did some decay equations. The decay constant, lambda, is simply the natural log of 2 over the half-life of the isotope, natural log of 2 being 0.693. So we use the natural log much more often than the actual log function. We talked about activity. Remember that activity is not the physical size of the source. It is just the activity, the radioactivity, the rate at which it is releasing energy. So that has a lot to do with the half-life of the isotope. You can have a large physical quantity, a physical weight of radioactive material, but if it has a very long half-life, it won't be that radioactive. And the flip side is true too as well. If you have an isotope that is very short-lived, you can have a very, very small quantity. You can have micrograms, microliters of a solution that can still have curies of material in it, the curies of activity, because it's just such a concentrated high, they say high specific activity isotope. So this is how you relate activity to actual physical number of atoms present. And that's through Avogadro's number. We don't need to get into that too much, so that's a little bit beyond, I think, what you guys need to know. Remember the decay equation, though. Your activity at time point t equals your initial activity times e to the negative lambda again being the natural log of 2 over the half-life. Yeah, so you substitute it in there. Remember that this works for activity. This works for dose rate as well. If you want to solve for t, you got to do a little algebra, or you got to get rid of the e. So first you would divide through by a0 or a0, which would give you AF over A0, and then you have E isolated. So once you have that, then you can take the natural log, and that's where this looking equation comes from. The natural log gets rid of the E on this side, and this will just be a constant. If you're looking for T, you should be given a final activity and initial activity. So that the only variable left is the T. So you just got to divide through. You should have a known half-life, in which case these would be a constant as well. So you'd have all constants with T. You just got to get T isolated, and that would give you your answer. Effective half-life, different than physical half-life. As soon as you put a radioisotope into a living body, there will be some biological removal in combination with that physical half-life. So if you know that biological removal, you can calculate what the effective half-life is. So we use this a lot in treating certain patients because we want to know how quickly the radiopharmaceutical is going to leave the body to decide how much to actually give the patient. So a lot of times they'll give them a dosimetric dose, which is essentially just give them a small amount of the isotope they're going to use and then see how long it kicks around in their body. And then they can decide how to use how much of the big dose to do. Gamma constants are important. We use them in relation to shielding, but also just a gamma constant really is just the amount of radiation at a certain distance that an isotope gives off for a certain activity. So some isotopes will have many more gammas per decay. They might have high energy electrons. So mostly it's just the actual number of gammas that the isotope gives off dictates its gamma constant. So something like cobalt 60, because it has two high energy photons per decay, and they're both 100% abundance. So that means they're both, every single decay is giving off those 2 photons, means that it has a high gamma constant. For something like I-125, which has lower energy gammas in some x-rays, but they're less abundant. Not every decay has one of those gammas, so it'd be much lower. The inverse square law, important to be able to do this. Remember that if you create a little bit more distance, you reduce the dose by a lot because it's the square law. So, if you double your distance, it's 4 times less radiation. If you triple your distance, it's 9 times less radiation. So this is useful in conjunction with the gamma constants because this is, remember, it's a certain intensity radiation at a certain distance. So if you want to know a different distance, you need to be able to manipulate the inverse square law to get to the distance in question. We did shielding and attenuation of radiation. So this is where the gamma constant comes into play. And then in conjunction with the number of shielding, it's similar to the decay equation, but you have this mu in place of lambda, and the mu is the attenuation coefficient, the linear attenuation coefficient, which is, yeah, so natural log-2 over the half value there versus natural log-2 over the half life. So there's a lot of similarities there. You just have to make sure you have the right mu, because there's linear attenuation coefficient and there's mass attenuation coefficient. But linear is the one you want to use in this situation, especially because you think of the linear attenuation coefficient is per distance. That's the unit. It's, centimeters to the -1. So it's really just the amount that the radiation is attenuated per unit of distance. Just like the decay constant is the amount of material that decays per unit time. So there's a lot of analogs between shielding and just decay. So the attenuation coefficient is nuclide specific because they all decay with a different energy. So something that's very low energy will have a comparatively high mu, because that means that a lot of the energy coming from that isotope will be stopped by a certain thickness of lead or whatever material you're going with. This is for lead specifically. So it takes a very little amount of lead to stop I-125 photons. Contrast that with something like cobalt-60, which you need a lot of lead because it's a high energy photon. Half value layers are, the amount of material you need to reduce the intensity of radiation to half that level. Again, very similar to half-life, but you're going to have half value layers for different energies and different materials. So you need to know the energy and the material in order to get an accurate half value layer. 10th value layer is similar. It's just instead of half the radiation level, it's the amount of material you need to attenuate to 10 times less radiation level. So we talked about shielding design, and you remember this transmission factor B that really dictated how much shielding that you need. B equals PD squared over what? We had to go through. So P is your dose limit in question. It's that if it's controlled area versus uncontrolled. D is the distance from the source, the workload, the use factor, and the occupancy. So those three are very important. Those are all what dictate how much, the intensity of the radiation and how much you need to reduce that radiation at a certain point. And that will give you that transmission factor that you can then take to, we'll get ahead of ourselves. So take that transmission factor, and then that will give you the number of half value layers that you need, from which you can calculate, how much actual material you need. If you know the half value layer and you know the number of half value layers, that gives you the thickness of material that you need. So just looking at the limits, remember that for a controlled area, it was 10 millirem per week. It used to be 100 millirem per week, but then it was changed to, reflect that you may have pregnant staff. Also just the ALAR principle in general, just because you can get 5,000 millirem in a year doesn't mean you want to be working outside a LINAC vault that is designed to give employees 5,000 millirem in a year. Just because you can, it's not prudent to do so. For uncontrolled, it's at 2 millirem in a week, with 50 weeks in a year corresponding to 100 millirem, the member of public limit. But also you can't have more than 2 millirem in any hour. Occupancy. Remember that certain areas are occupied all the time. The console, if the machine's on, you would assume someone's at the console, so that would be a 100% occupancy or a 1 for occupancy. Whereas something like a hallway or a toilet or something, the odds are that every time the machine's on, it's the same person in the toilet every time. Is not very likely. It could be occupied, but it's not going to be the same person getting the same dose. So you would treat that with a much lower occupancy than something like the console. Okay, and that's the midterm review. I will have a second part for the final review shortly.